Okay. Hello everyone. This is Dr. Rajesh Prasad. I am working as a professor in Ajay Kumar Garg Engineering College, Ghaziabad. So I am going to discuss the traveling salesman problem using branch and bound approach. So this TSP is a very classical problem. So and it is almost coming into the category of NP hard problem. It is not solvable in polynomial time. So that's why we try to find out various solutions of this approach. So one of the very popular approach is branch and bound together with backtracking. So but branch and bound is going to be like optimization problem. Backtracking is a permutation problem. So we are going to discuss branch and bound solution of this TSP. And next one, how to get approximation algorithm solution. So let's like have a little bit briefing of this TSP, and then we'll talk about branch and bound technique, right? Then we'll start understanding the problems. Okay, so what is actually here, a set of some cities are given in TSP, and distance between every pair of cities are also given to you, right? So in most of the time, like cities are modeled in a graph, and this can be like cities can be treated as a node like this, right? So so what is TSP? It states that a salesman has to visit every city exactly once, right? Every node has to be visited exactly once. Remember that edges can be repeated. Edge is not a problem. Vertices, every vertex you have to visit. No vertex should be left, right? And one vertex should be visited exactly once, right? So he has to come back to the city from where he starts his journey. Okay, so what is the shortest possible route that the salesman must follow to complete his tour is the problem of the TSP. Okay, and you might have heard about Hamiltonian cycle also. So let us like Hamiltonian and Euler. Like Hamiltonian cycle is not like optimization problem. It is not minimizing or maximizing, but it is the same as TSP, that you have to visit every vertex exactly once and you have to come back at the beginning. Hamiltonian cycle is for like non-weighted graph, while in Euler circuit it is this like a circuit which visit every edges exactly once. Vertices can be repeated. So you got the difference between Euler and Hamiltonian. Both Hamiltonian is nothing but like not weighted TSP. Okay, and Euler exactly each edges we are visiting exactly once. Vertices can be repeated. Okay, so this is an example. If you understand it, like see here, suppose we have a city, like, and if we have cities, so and they are connected graph, of course there should be connection. If you don't have connection, that means TSP is not possible. See, so you have see this A to B, and this is going to be 10, and then B to D is going to be 25, D to C, if you take it, it is 30, and then C to A, you take it as a 15. So if you find out this, it is 80 unit, but remember it is not going to be minimum. Minimum can be anyone. It may not be minimum cost. Okay. So uh, we are going to discuss TSP using branch and bound. Look at here, the two approaches. One is backtracking and the other is branch and bound. Branch and bound is very like backtracking actually follows DFS, depth first ordering and depth first search, while branch and bound follows BFS. This is not following depth first approach. This is always following breadth first search technique, and it is using so many optimizations criteria, like just its name suggests bounding function. So it is also using bounding function to kill the node, And this is also using least cost search method to kill the node. Like if you start from a particular node, going multiple one is not like all the options are going to be explored. Only one option is going to be explored in the VFS. So which option is going to be explored depending on the bounding function, that okay, if this cost is giving like out of C, suppose if you start from 1 going to 2, 3, 4, 5, so one has a cost, right? One has a cost, and every like children, they have cost, right? So what actually we are going to compute, we are going to compute a minimum cost from here. We follow this one. Suppose this is the minimum cost, then we will discard it here, we will discard it here, we will discard it here. So we will follow this approaches actually. So this is how the branch and bound is working. So let's understand this. So if suppose we have 4 node graph A, B, C, D. So these are the graph, and make a like adjacency matrix of this graph. A particular edge is not existing, we mark it infinity. Otherwise, like see here, A to B. A to B is 4, so this is written 4. A to C is going to be 12, so this is written 12. Okay, so after making this adjacency matrix, remember here I to I is infinity, right? We assume that node I to I is not reachable, so mark it in infinity together with any vertex like B to C. B to C, there is no directed edge, so mark it infinity, right? So after making this matrix, we apply the row reduction and column reduction techniques, right? So in the like here, first one, so row reduction technique and column reduction technique. What is row reduction technique and column reduction technique? From the row, actually, a row can be reduced if it is not having 0. Remember, a row or column can be reduced if it is having non-zero values. Okay, so suppose here minimum is, we take minimum value. Okay, so 4, 12, 7. So what is minimum here? Minimum is 4. Okay, and what is minimum here? 5. This is 5. What is minimum here? This is 6. And what is minimum here? This is 2. So that means we can reduce the row. Okay, so reduce means subtract this one by 4, subtract this by 5, subtract this by 6, subtract this by 2. Okay, so after reducing it, we will see that this guy is getting this. After row reduction technique, we are getting this value, and we mark it, we compute this, how much cost was involved in reducing the row, right? So we see that this is 4 plus 5 plus 6 plus 2. This is going to be 7. Okay, so row reduction cost is 17. After row reduction, we are entering into the column reduction, right? So there is no column here, like there is 1 0 here, so it cannot be reduced. Similarly, this cannot be reduced, but this can be reduced, right? Because it is having 1, this cannot be reduced. Okay, so if you reduce the column C, this is the final matrix. Okay, so this is initial matrix which you are going to start with actually, right? So you see here column was 1. So total cost, initial matrix cost of node number 1, we start with node number 1. So if we start with node number 1, what is its cost? Its cost is 18. Okay, 17 plus 1. Remember, up from 1, you can go to 2, you can go to 3, you can go to 4. There are 3 options from 1. Remember? But since cost is 18, this cost cannot be lower than 18. So this is the minimum cost which you have established in the branch and bound technique. Okay. So now if we start from like this is A in our own terminology, this is B, this is C, this is D. So cost of node number 1 is 18. So from here you can go to A to B or A to C or A to D, depending on which one is minimum. by taking this one as the cost matrix. See this is your cost matrix, like yes, so this is the initial cost matrix. Now if you start from A to B, what will happen, A to B. So in this situation, look at value of A to B. A to B is going to be 0. You record it 0. Okay. So what is next step? Make row A infinity. Okay. Row A infinity, because we are interested in A to B, and column B infinity, because this is the transformation. Row A infinity, column B infinity, and then B to A, definitely, A to B, then you are going to back from B to A. So B to A is also going to be changed to infinity. These are the transformation if you are interested from A to B, right? So if up you see here, so this is the one, you see, row A we did infinity in this, so this is infinity, column B is infinity, rest remain the same thing. This is the transformation. Okay, B to A is also going to be infinity. So three major changes you are going to do if you are going to do from A to B. What is the major changes? A to row A infinity, okay, number one. Number two, column B infinity. Number three, since you are going from A to B, definitely you have to come back from B to A. So this B to A is also going to be infinity. After doing this transformation, this is your matrix, right? Okay. Again, you have to start reducing it. So row reduction, this cannot be reduced because everything is infinity. So this row cannot be reduced. Similar, but this row can be reduced. What is minimum? 13. This cannot be reduced. This cannot be reduced. So, this is the row reduction. Okay. So after this row reduction, this is the answer. Okay. So you record this value as 13. Okay. After row reduction, you start with the column reduction. There is no, this cannot be reduced. This cannot be reduced. Similarly, this cannot be reduced. This cannot be reduced. Okay. So this cannot be reduced. So what was the cost? 18 is the cost of node number 1 plus 13 is the cost of row reduction. Okay. So you look at here, 13 is the cost of row reduction. Okay. So, and then this is the column reduction is like also going to be here. So this total cost is going to be 36. Okay. So, if like this is the number 2, this column can also be reduced. Okay. This column was reduced by 5. Okay. So this is how it is 5, and row was reduced to 13. Row was reduced to 13. So this is becoming 36. That means if you are coming from A to B, this was 18 and this is 36. Now let us explore another option C and let us explore another option D. By taking the original matrix, this number 1 matrix is going to be again. So if you are going to A to C, row A, column C, and then C to A going to be infinity, right? So let's see this. Yeah. So row A infinity, column C infinity, then C to A is infinity. These are the changes you have to do, right? Okay. So now no row reduction, no column reduction, no row reduction here, no row reduction here. So row reduction is not feasible. Similarly, column reduction is also not possible here because we have 0, we have 0, we have 0, we have 0, right? Column reduction is also not possible. So what is cost over here? 18 was the previous one. But if you look at here A to C was here in this matrix. A to C was 7, right? So this guy is going to be added. 18 plus 7 become 25. So that means this is going to be 25. Similarly, if you start with A to D, A to D in the same matrix, A to D in the same matrix here. Row A, infinity, column D infinity, and then D to A infinity. So if you look at here, so A to D, this is the row A and column D and D to A infinity. Again, you start with the row reduction technique. So this is going to be no reduction, but there is a reduction of 5, no reduction. So okay, and then after doing this, look at here, this becomes 0, and then you see there is no column reduction, no column reduction, no column reductions. Okay, so this cannot be reduced. So what will be the cost? A to D was 3, right? A to D was 3. So if you just start with this computation, 18 plus this reduction was 5 plus A to D was 3. Okay, so 18 plus 5, 23 plus 3, this become 26. So this is the summary of this. Cost of node number 4 is 26. So you have 136, other 25, other 26, right? Yeah. So this guy is 26. That is it. Simple. So using branch and bound technique, of course, this is going to be discarded. This is going to be discarded. So only we are going to explore A to C. That is it, because this is the minimum. Okay. So now if you start the same technique, C and then C, A to C. So we have two options, C to B and then C to D, because we cannot, we have already included the A. So this is the option A to C, C to B, then C to D. Remember, we while computing C to B, we have to take this matrix which was giving you 25. This is the matrix for next computation, right? This is the matrix. Okay. So yes, so now we consider the matrix of node number 3. This is the matrix. Okay. So again, you see here, choose the row reduction, no row reduction, no row reduction, no row reduction. Similarly, no column reduction, no column reduction, no column reduction, no column reduction. Clear? Okay, so if you look at here, you started from A, then C, then CB. Look at here, C to B, it is infinity. Okay. So of course, no, there is no A to C, cost of C was 25 plus C to B is infinity. This is infinity. Okay. So that is why it become infinity. This is infinity value. Okay. So see here, see, cost of 5, 25, 13 plus this become infinity. Okay. So that means, here, yes. So, okay. So this was actually, once we take this, so we are interested in C to B. Okay. So this row C need to be infinity, column B need to be infinity, and B to A, BA, matrix of BA need to be infinity, right? So B to A infinity, and then row C infinity, and then column B is also infinity. This is the one. We are going to compute the row reduction from here. So no row reduction, 13, and then no row reduction, and then 8, right? So this is how we have computed the value, and now you see this is the infinity. Okay, so that means this is not the feasible one. Similarly, if you start with C to D, same node number 3 value, we are interested from C to D. So row C is infinity, column D is infinity. Okay, and then D to A should be infinity. This should be infinity in node number 3, which was giving 25. Okay, so you see here its cost is still 25. That means this is the possible exploration. This is infinity, this is 25. So A, C, D, and of course now you see here, now this is the approach. Okay, so this is the final one. C to D is 25. That means this is the path. Okay, so you have to take this matrix. This matrix is the one final. So now next node is like you got A to C, C to D, and then of course D to B. Okay, row D infinity, column B infinity, and then B A infinity. This is the infinity. So entire matrix, and then you know like D to B is 0. Okay, so you see here, after doing this, you will see that this 25, this cannot be reduced. Entire matrix will be infinite actually. While doing this, you will see that entire matrix will be infinity. This is 0, and sum of no reduction is 25 actually. So overall cost of the salesman is 25. And what is the path? We got it, A to C, C to D, and then D to B and B to A. This is the salesman tool, right? So same thing, if you just go to its analysis, it is also going to be n factorial. And we know that this is very NP like hard problem. So if you understand its approximation solution, it will be easier, because you know in approximation you may not get exact solution, but problem can be solved in near optimal, near like polynomial time. So this approximation is only eligible working if you have triangle inequality. What is triangle inequality? That if you start from I to j via k, so dij is always less than or equal to dik plus dkj. If we follow triangle inequality, approximation can give you the solution. So this is very important techniques. Like let's have an example. Like see, suppose this is the one is starting from 1. So here you find out minimum cost spanning tree using prims. Why prims? Because in prims we are always getting tree, we are not getting graph, right? We are not getting forest. After taking this MST, compute, like after taking this MST, take the pre-order traversal, DLR traversal, right? So once you are done with the DLR traversal, you will see that this path is going to be the optimal. Like see here, data left, right? So 1 data, then go to 2, and then 2 to 4, and then 4 to 3. This is the cost actually. So 1 to 2 is 10, then 2 to 4. Data left, data left, then right. So this you can convert it into the binary tree, right? Then 2 to 4 is 25, 4 to 3 is 30. Remember, you may not get optimal solution, but it will be near optimal solution. Okay. So by doing this, you can get the near optimal solution. This is very important problem. So here is the reference that you can follow the Corman, and or you can just follow the Horowitz-Sani also. This is also given like giving the branch and bound solution. Thank you.